Good afternoon, students. So in the previous class we have learned about the calculation of magnetic moment by spin only formula and then spin and orbit angular momentum. Okay. So today we shall discuss about comparative treatment of 4D and 5D series with their analogues. Alright. First point is ionic radii. The atomic and ionic radii of elements of 3D series are always smaller than 4D and 5D series. Okay. Now what is the reason for that? Because 4D and 5D series one more shell is added. Correct. 4D and 5D series are found below 3D series. Correct. So n value increases as you move down, the principal quantum number value increases. Okay. So 4D and 5D series, since they lie below 3D series, okay, 3D series, the atomic and ionic radii, okay, of this series is greater compared to what 3D series. Alright. The 4D and 5D series elements have similar size due to Lanthanide contraction, but 4D and 5D series have got similar size due to what? Lanthanide contraction. You are going to study, okay, in the next part what is Lanthanide contraction. Alright. In the case of 4D and 5D series, filling up of 4f orbitals will be completed, okay, before 5D orbitals. So in 4D and 5D series, filling up of 4f orbitals will take place first, okay, before filling on 5D orbitals. Alright. The electrons of f orbitals are not effective in screening other electrons from nuclear charge. The f orbital electrons are not that much effective, okay, in screening the other electrons from what? Nuclear charge. Therefore, gradual decrease in size of the lanthanide elements taking place, or that is known as what? Lanthanide contraction. Okay. So we shall move to the next slide. Second point, oxidation states. In the case of 4D and 5D series, the higher oxidation states are more stable and are less oxidizing. Okay, here is an example. Ruthenium and osmium exhibit maximum oxidation state of +8, okay, in their tetroxides. Now what is the formula of tetroxide? For example, osmium tetroxide is OSO4, okay, and what is the oxidation number of osmium? +8. Why it is +8? Oxidation number is -2. Okay, -2 into 4 is -8. Therefore, in order to have 0, so, addition you should get 0. Oxidation number or sum is equal to 0. Correct. So +8 -8 is equal to 0. Okay. So +8 is the oxidation state of osmium. Alright. In 3D series, +2 and +3 are the most common stable oxidation states. You know that. Okay. So for example, manganese is present in 3D series, okay. So most common oxidation state is +2, okay. Similarly, most common oxidation state of iron is Fe, that is +3, okay. Iron oxidation state, most common oxidation state is +3, okay. So this is observed in 3D series. Alright. So next slide. Third point, magnetic behavior. In the case of 3D series, magnetic moment is due to only spin of motion of the electron. Okay. How do you calculate magnetic moment in 3D series? Due to spin motion only. And what is the formula for magnetic moment calculated by spin motion? Mu(s) is equal to square root of n into n plus 2. Okay. Bohr magneton. What is n? It is the number of unpaired electrons. Okay. One Bohr magneton is equal to Eh by 4 pi mc. E is the electronic charge, H is the Planck's constant, m is the mass of the electron, c is the velocity of light. Alright. Whereas 4D and 5D series, magnetic contribution is due to what? Both spin and orbital motion. Okay. Therefore, you need to calculate magnetic moment by which formula? Landis formula. Right? Landis formula. What is Landis formula? Mu(s) plus L is equal to square root of 4s into s plus 1 plus L into L plus 1 Bohr magneton. Okay. What is S? Total value of spin quantum number, right? L is total value of orbital angular momentum. Okay. Next slide. Fourth point, stereochemistry. Due to bigger size, 4D and 5D series elements form complexes with higher coordination numbers. Okay. Higher coordination number. So here is an example, okay, element which shows higher coordination number. For example, zirconium, okay. In zirconium, heptafluoride, that is ZrF7, okay, 3 minus, has coordination number 7. How do you say that coordination number is 7? 7 monodendrite fluoride ions are present, correct? So coordination number is 7, okay. And what is the shape of the or geometry of the molecule? Pentagonal bipyramidal, okay, pentagonal bipyramidal. Similarly, another example, UF8 3 minus, okay, 8 fluoroligands are there, okay. So minus 8, therefore uranium, okay, uranium, what is the coordination number? Coordination number is 8. Why? 8 fluoroligands are surrounding uranium atom, okay. So it has got cubic geometry. Geometry is cubic. This is due to greater interaction of d orbitals with the ligands to form low spin complexes. So these show what? Low spin complexes. Low spin complexes are also called one strong field ligand complexes. Okay, strong field ligand complexes. 4 coordinate complexes of these elements are square planar. Okay, example for square planar complexes: palladium 2, platinum 2 and gold 3. Okay. In the case of 3D series, 4 coordinate complexes are either tetrahedral or square planar. Okay. Which are those? Example: nickel 2 plus, cobalt 2 plus and then copper 2 plus. Okay. Next slide. Chemistry of F block element. So far we are discussing about chemistry of D block elements. Okay. So now we shall discuss F block elements. Now which are called F block elements? Lanthanides and actinides. Okay. These are called F block elements because differentiating electron or valence electrons enters into F orbital. Alright. There are 2 series of F block elements, 4F series and then 5 series. Okay. Now which are the elements of lanthanides? Alright. Which are the elements of lanthanides? Correct. Lanthanides, lanthanum atomic number is 57. Okay. Lutetium atomic number 71. Correct. Lanthanum is the first element, lutetium last element. Similarly, actinides, actinium is the first element. Okay. Lawrencium is the last element, 103 atomic number. So the elements are placed at the bottom of the periodic table. Okay. You can see here lanthanum to lutetium. Okay. All the elements of lanthanide. Similarly, actinium to lawrencium, all the elements. Alright, all the elements. So next slides. F block elements are those elements in which a differentiating electron or valence electron filled up in n-2 F orbitals. Alright. So here electrons enter into n-2 F orbitals. Okay. Now in order to have 4F series, 4F block, you should have n is equal to 6, 6 minus 2, that means 4F, correct. In order to have 5F, 7 minus 2, okay, principal quantum number value is 7 or n value is 7, okay, so you get 5F series. F block elements are called inner transition elements, okay, they are also called inner transition elements, okay. There are 2 series of F orbitals, I have already told you, okay, which are those? 4F and 5F series or 4F orbitals and 5F orbital compounds. Okay. So each series having elements, lanthanide series, okay, outer electronic configuration is 4F 0 to 14. Okay. Why 0 to 14? There are 7 F orbitals, correct. Each F orbital contains 2 electrons. Okay. So 2 into 7 total or altogether 14 electrons, right. So lanthanide series 4F 0 to 14. Okay. Similarly, actinide series. Actinide series 5F 0 to 14. Here also F orbital is present. So total 7 orbitals. 2 into 7 is 14. Therefore, filling up of electrons from 0 to 14. Okay. So these are called also called actinoids. So lanthanoids and actinoids. Okay. Next slide. Lanthanide series 4F 0 to 14. Okay. They are called lanthanoids. Lanthanide series refers to the element that follow lanthanum. What is the atomic number of lanthanum? 57. Alright. Cerium atomic number 58. So cerium to lutetium. Okay. Cerium to lutetium. Atomic number 71. These have 4F subshell. Okay. Or 4F orbital. The general electronic configuration of lanthanides, okay, xenon 4f 0 to 14, 5d 0 to 1, okay, 6s2. Okay, this is the outer electronic configuration. That means n minus 2 f 0 to 14, n minus 1 d 0 to 1, okay, and then ns2. Alright, all the lanthanides have similar electronic configuration. Okay, all elements which you find in lanthanide series have got similar electronic configuration, similar chemical properties, similar oxidation state, and are placed separately at the bottom of the periodic table. Therefore, they are placed separately at the bottom of the table. Alright, next slide. Actinide series, they are also called actinoids, 5f 0 to 14. Okay, actinide series contains elements that follow actinium. Okay, what is the atomic number of actinium? Z is equal to 89. Starting element is thorium, starting from thorium, okay, ending with lawrencium. What is the atomic number? 103. These have 5 subshells. Okay, that means 5f subshell. The general electronic configuration of actinides is radon Rn 5f 0 to 14, 6d 0 to 1, 7s2. Okay, or n minus 2 f 0 to 14, n minus 1 d 0 to 1, ns2. Okay, this is the common, that means same electronic configuration which is found, general electronic configuration found in all actinides. Alright, most of the members of this are radioactive, okay, or artificially prepared in the laboratory. Almost all actinides, they are radioactive elements, okay, or they are artificially prepared in the lab. Okay, next slide. Lanthanide contraction. Now here in this, okay, part we are going to study what is lanthanide contraction and what are the reasons for lanthanide contraction. Alright, the values of atomic and ionic radii of lanthanide, okay, 3 ions, decreases gradually from lanthanum to lutetium. Okay, atomic and ionic radii of all lanthanide series elements decreases from lanthanum to lutetium. Okay, it was observed that on going from lanthanum 3 plus to lutetium 3 plus, ionic radius shrinks from 1.15 angstrom to 0.93 angstrom. Okay, almost to an extent of 20 angstrom. This steady decrease in atomic and ionic radii of lanthanides is called lanthanide contraction. Okay, so you will find that when you move from lanthanum 3 plus to lutetium 3 plus, the ionic radius gradually decreasing, and what is the exact value? 1.15 angstrom to 0.93 angstrom. Okay, this slow and steady decrease of atomic and ionic radii, that is called what? Lanthanide, that is called lanthanide contraction. Okay, you can see the graph over here. Okay, graph of ionic radius of elements. Okay, you can see gradual decrease in one ionic radius. Okay, next slide. Causes for lanthanide contraction. Now here we will see what are the causes for lanthanide contraction. As the atomic number increases along the period in the lanthanide series, 4f electrons are added, one at each step. Okay, you know that in a period as you move from left to right, atomic number goes on increasing, correct? As the atomic number goes on increasing, okay, electrons are being added to what? 4f orbital, correct? Because these are 4f and 5f series, right? Lanthanides are 4f series, actinoids are 5f series. So electrons are being added to 4f orbital in lanthanides. Similarly to actinides, 5 series. Okay. The mutual shielding effect of f electrons is very little. Okay. The shielding effect of f electrons is very little. That is due to what? Their shape. Their shape of f orbitals are in such a way that their shielding effect is less compared to the other orbitals. Okay. The nuclear charge therefore increases by 1 unit at each step. What do you mean by nuclear charge? The force of attraction by the outermost electron to the nucleus increases, okay, by 1 unit at each step. Hence the force of, as the nuclear charge increases, the force of attraction also increases, because number of positive charge increases at the center, right? At the center or nucleus, number of positive charge increases because the atomic number increases. As the positive charge increases, of course, the negative charge also increases, but the force of attraction increases. Okay. Therefore, the force of attraction by 4f electron towards the nucleus increases. This causes the reduction in size of the entire subshell. As a result, the entire subshell, there will be reduction in size. Alright, that is atomic and ionic size goes on decreases as we move from lanthanum to lutetium to an extent of 2 picometer. To an extent of 2 picometer. It was observed that on going from lanthanum to lutetium 3+, the ionic radius shrinks from 1.15 angstrom to 0.93 angstrom. So this much shrinking will be taking place in ionic radius. Alright. This steady decrease all along the series of lanthanides is called what? Lanthanide contraction. Since there is a decrease in ionic radius, so this steady decrease in the ionic radius of lanthanides, that is called what? Lanthanide contraction. Now what are the consequences of lanthanide contraction? Due to lanthanide contraction, there is similarity of atomic radii of second and third transition series. Atomic radii of second and third transition series, that is similar. Second point, separation of lanthanides from their mixture is possible due to lanthanide contraction. You can separate the lanthanides, elements belong to lanthanide series from their mixture, due to what? Lanthanide contraction. It is possible, separation of mixture is possible. Next point, due to lanthanide contraction, there is a variation in basic strength of hydroxide. Basic strength of hydroxide, there will be variation. What is the reason for that? Due to lanthanide contraction. The basic strength of hydroxide decreases from lanthanum hydroxide to lutetium hydroxide. So basic strength decreases. Lanthanum contraction is responsible, responsible for what? The strength decrease, basic strength decrease from lanthanum to lutetium. Alright. Next, consequences of lanthanide contraction. What is the consequences of lanthanide contraction? Similarity of second and third transition series. The atomic radii of second series, that is 4D series of transition elements, are almost similar to third transition series. Atomic radii of 4D series is similar to 5D series. Example is given here. Atomic radii of zirconium is 1.45 angstrom and hafnium is 1.44 angstrom. Alright. Here the usual increase in size on moving down the group from second to third transition series is cancelled by the decrease in size due to lanthanide contraction. Whatever increase is taking place from moving down, that will be cancelled by the decrease in size. How decrease in size taking place? Due to what? Lanthanide contraction. Alright. Next point, separation of lanthanides. Separation of lanthanides is possible due to lanthanide contraction. All the lanthanides have quite similar properties, and due to this they are difficult to be separated. However, because of lanthanide contraction, their properties such as ability to form complexes vary slightly. The other properties they have got similarity, but in complex formation, the properties are not similar. All lanthanides, the properties in forming complexes are not similar compared to other properties. Therefore, they can be separated. Lanthanides can be separated. This slight variation in property is utilized in the separation of lanthanides by ion exchange method. So this you are going to study in detail in the next class. Alright, ion exchange method. Now in the ion exchange method, lanthanides can be separated. How they are separated? By one complex formation tendency. Alright. So in all the other properties they are show similarity except one complex formation tendency. Therefore we can separate lanthanides by which method? Ion exchange method. Third point, the basic strength of hydroxides decreases from lanthanum hydroxide to lutetium hydroxide due to lanthanide contraction. The size of M+3 ions decreases and there is increase in the covalent character of MOH bond. the strength of hydroxide decreases. You know that. Why the strength of lanthanum hydroxide to lutetium hydroxide goes on decreasing? Due to lanthanide contraction. Okay. So due to lanthanide contraction, strength decreases. Okay. So since the strength decreases, the covalent character increases. So the size of M plus 3 decreases, and there is increase in covalent character of MOH bond. So in between the metal atom or the F-proc element metal, M is any lanthanide element or actinide element. Okay. So in between lanthanide or actinide element and the oxygen, there will be one covalent bond present or increase in the covalent character taking place. Okay. Next, fourth point, existence of 3 pairs of elements. Lanthanide contraction is responsible for the existence of 3 pairs of elements. Now, which are the 3 pairs of elements? Zirconium and hafnium, niobium and tantalum, molybdenum and tungsten. You can see in the tabular column. Okay, you can see the diagram. Zirconium and hafnium. Okay, below zirconium we have got hafnium, and then niobium and tantalum. Below niobium we have got tantalum, and molybdenum and tungsten one below the other. Okay, these pairs of elements possess almost equal atomic radii, equal atomic volume, and same number of valence electrons. Okay, so therefore there exist 3 pairs of elements. Okay, due to what? Lanthanide contraction. All right. So I will stop at this stage. Okay. Any clarification, you may contact me. All right. Please go through all these slides. Okay, and clarify your doubts. Thank you.